Let us have a brief look at the construction of a capacitor. So, while we know that we are going to treat the capacitor as a circuit element where we are interested only to have a current flow inside the element and come out of the other side. And in this process, there should appear a voltage across the element. So, in this view of a capacitor is basically constructed by having two conducting plates separated by a material that is an insulator or or a material with a very high resistance. So in an ideal capacitor model, this resistance is considered to be infinite and no current is allowed to pass through these plates. And these two plates is the word used for these two conducting materials. These two plates basically are made up of conducting material, good conductors. And there is a high resistance or insulator or low conductivity element in between. This material that is placed between the plates is usually also referred to as the dielectric material. So this is very interesting because on the one hand we are saying the current flows into the element and should come out of it, but if there is such a high resistance between these two plates, so while the plates are conducting, they are not touching each other. There is a high resistance material between them. So if there is a flow of current into this, how can current flow to the outer terminal? And how would the current flow in this open circuit in a way? So this is very interesting. But let us look at the physics of this thing very briefly. So there is a wire that is conducting, that is carrying a current flowing to this plate it is connected to, and then there is a dielectric material between the capacitors. I am just trying to exaggerate a bit. And then there is other plate and a wire connected here. So suppose for a moment that this is a wire. So we have a current flowing to, let us assume this thing is connected to a supply that is providing a current flow through this capacitor. And we know the current that we take, we assume that it is a flow of positive charge. So positive charge flows up to this plate. This is the current I. It reaches this plate, and because there is nowhere to go, it gets deposited or collects here on this plate surface. So positive charge gets deposited, or we get an excess of positive charge here because current positive charge is flowing into this plate. So it gets deposited here. So if you consider this plate as a big node, so then there is current flowing into this, but where is the current going? So what about KCL, Kirchhoff's current law? So KCL does not hold here. So that cannot be the case. So lucky for us, that Maxwell came up with unified electromagnetic theory, and he come up with this idea that whenever there is a changing voltage or say changing electric field, there is the concept of a displacement current. So although current does not flow within this dielectric material, but because of the accumulation of this positive charge here, this dielectric will displace some charge, and negative charge is going to be collected on this end of the dielectric material because like charges attract each other, and the positive charge will be collected on the other end of the plate. So if the negative charge basically move from here to here and the positive charge move from here, so some sort of a current flows within this dielectric material. There is no current flowing from this plate to this material. This is very important. This current is flowing inside this material only, and it is flowing inside the capacitor. So this is an internal current. This current coming from outside, this is an internal thing. And Maxwell basically, uh, based on the Maxwell magnetic electromagnetic theory, we can call this current the displacement current. So displacement current flows in the dielectric material inside the capacitor, and because we have this positive charge in the dielectric material this end, we are going to get an accumulation of negative charge in this plate, because it is going to attract, or in another way we can say this positive charge is going to push the positive charge to flow out from this, and the same current I will flow, because Maxwell found that this displacement current is equal to the current, let us call that the conduction current, the current flowing because of conduction. So charge moves here, here charge displaces itself, and charge flows out of it. But looking from our point of view, what we need is actually achieved. We got the current flowing into the element and the current flowing out of the element, and that's what we require. So how this happens inside is can be explained in a greater detail in a course of physics, but from circuit analysis point of view, all we are concerned is I is equal to C dV by dt as the Ohm's law type basic equation that governs a capacitor. And the C, as we have seen, is the capacitance. So capacitance basically depends on how the capacitor is formed, what kind of dielectric is used, how close the plates are, how big the plates are, and several other things, but we can sum all of them up in this expression. So C is equal to epsilon A over D, where A is the area of the plates face, the area that the plate shows to the dielectric, and this D is the displacement between the plates, and epsilon is termed the permittivity as a property of the material used as a dielectric. So for example, the permittivity of air or free space is 8.854 picofarad per meter. So generally in the construction of capacitors, uh, the materials that are used as dielectric have very high permittivity, much higher than this, because we don't want to have very huge sized capacitors. So to bring down the size of the capacitor, or a capacitor with a large capacitance, either we increase the area, decrease the D, the displacement, the spacing between the plates, or increase this permittivity. So high permittivity materials are used, and so that high capacitance can be achieved, or the size reduces. Remember, I told you that 1 farad is a huge capacitance, usually not used in real life in most of the circuits, and we come across a few hundred of microfarad, and which is still a large capacitance. We typically deal with nanofarads and few microfarads and picofarad capacitors in this range, which is more normal size capacitors. You can look up in the book to have a picture, or in the lab, for example, you can see these capacitors being used. Okay, so this is a little bit about the construction of a capacitor. Remember this very important thing, that a capacitor is an energy storing device. So how does this energy get stored in the capacitor? So whenever we provide a current an external current to flow through a capacitor, it charges it. So there is a mechanism we term as charging a capacitor. So when initially there was no charge, no positive charge here, no negative charge here, and we supplied the current, we got this positive charge here, negative charge here, and the capacitor got charged. So when the capacitor was not charged, there was no energy stored in the capacitor. But when it got charged, there will be energy stored in it. So what happens when we have positive charge here and negative charge here? We get a voltage difference between these two plates. An electric field sets up between these two plates and we get a voltage difference. So whenever we have a voltage difference between the two plates or voltage across a capacitor, we say it is charged, it has some energy. When we increase the voltage, we increase the electric field strength between the two plates and we increase the amount of energy that has been stored in the capacitor. So this means the energy stored, we use W to represent energy. Energy stored should be proportional to the voltage across the capacitor. So we can see that very clearly. And one important thing, as the current flows into this capacitor, this charge on this plate, one plate, keeps on increasing and increasing. Overall, if we see this capacitor on the whole, the total charge on this capacitor is zero because this is positively charged, the same amount of negative charge here. However, if we look at one plate, then the amount of charge that has flown into this capacitor can be found by this expression I is equal to dq by dt, how I is defined actually. So we see that energy, we will see later on inshallah, that the energy that is stored in the capacitor is somehow related to the voltage across it. So if we have zero voltage, no energy is stored there. But if there is some voltage, then in order to increase the energy stored in the capacitor, we need to increase the voltage. For that, we have to supply more current or more charge is stored. We are going to come across these expressions later on, and we will have better relationships between these quantities for the case of a capacitor. So I hope this much of detail about the construction of a capacitor will explain the basic curiosity of what happens.